All right. Hey guys, again, I just had class with you guys and you informed me that the video that I had filmed for this already didn't have audio. So I apologize for that. I'm filming it again because, again, these are notes that I want you to take in section 1-3. You could just read the textbook, try to take notes, but I think it's more helpful to you to have a teacher walking through things with you because there's really 5 things in this section that get covered. And with that, like I got to talk about each for like 5-10 minutes because some stuff can be confusing. Maybe you're not used to writing out some ways that you'll need to write this out and refer to this in the future. Okay, so there are actually 6 things here. So what we're going to do in this here, we're going to start with some definitions, talk about exactly what an angle is and what some parts of angles are. Secondly, we're going to talk about naming an angle. There is a naming convention that you need to be aware of and how angles get named and what inappropriate names could be. Number 3, we're going to talk about the measure of an angle. I guess you probably know that angles get measured in degrees, but how do you write about angles measurements? What's the proper way to write it? What's the proper way to report it? And what are the rules around it? Okay. And then after that, we're going to talk about some rules, right? We're going to talk about some rules. Those are postulates, right? Postulates related to angles and what we can do with their measurements. What are some things that we need to assume and then use in the future? And then finally, we'll have some more definitions at the very end here. Okay, so let's go ahead and jump into it with that very first thing, which is talking about what the heck an angle is. Also, another thing that I forgot, we're going to talk about what the 4 different types of angles are. So that's a 6th thing that we need to talk about here because there are 4 different classifications of angles. You might know a few, but you want to know them all. Okay, and in addition to reading, I think just talking about it too could be helpful for some people. All right, so anyways, we have an angle here. When you see this symbol, that means angle. So that is the angle symbol right there. And an angle is a figure that is formed by, well, they're formed by, what do I have here? What do I have here? Rays. 2 rays to be specific. Okay, and these just aren't any rays. Let me start by just kind of drawing a ray right now. Boom, boom. We have here O, and we have here A. So this is ray OA. And if I drew another ray right here, that would create an angle, but it wouldn't create an angle that is just one angle. That would create more than one. Anyways, I'm saying kind of a lot here. I could draw another ray right here, for instance, that's parallel to this ray, but that wouldn't be an angle here. Okay, so remember, when we're coming up with definitions, we need to classify something in terms of what are the figures, and we need to differentiate it. And what an angle is 2 rays that meet at a common, what do we call that? For this ray. And for this ray, we'll call it OC right here. They meet at the common endpoint, have the same endpoint or common endpoint as you'll see there. And that's what an angle is. An angle is here. Okay, so here we have angle AOC, and I'll put angle AOC right here. For you politics fans, you might recognize that, angle AOC. Good old Alexandria Ocasio-Cortez, kind of naming it for her there. Anyways, but this is how we say this out loud. Angle AOC, and that's what we have to do here. So this tells us that a lot of angles get named through 3 letters, right? 3 letters, and one of which is an important letter in the middle. We're going to talk about this one in a second, what O is for this particular diagram here, okay? So in this diagram here, we have an angle AOC. The 2 what are we talking about here? We're talking about rays. The 2 rays are called the sides of the actual angle themselves here. So we have our sides, and that's this, right? OC, okay, and AO, right? AO, those are the sides, okay? Their common endpoint, right? Their common endpoint right here gets a special name for particular. We don't just call this the common endpoint, but I'll put here common endpoint. What this is called the, let's read here, called the vertex, okay? So this here is the vertex of the angle, and right, these here, the rays themselves are the sides here and here, okay? And those are the 2 things here. So if you look at the naming convention right here, just to give you a little hint here, you're always going to see the vertex point. So remember, a vertex is a point. It's just like Algebra 1, where you've heard of vertex before. A vertex is part of a parabola, right? Parabola, it's the highest or lowest point of the parabola. So vertex is kind of the one special point of a parabola, or the most special points on a parabola, because they have more than one special point, but it's the special point on the angle itself. We'll call that the vertex of the angle here. It appears in the middle of the name. We'll talk about the names a little bit later here. Oh, we'll talk about names right now. Let's do it, okay? So a name of an angle can have up to 4 names right here. I told you this was AOC right here, but I also could have named it angle O. So let's go ahead and go through this together right now for angle TAP. So this can be called angle TAP. It can be called angle PAT. If you're writing these down, you're going to write these 4 with me here. It can also be called angle A. And finally, it can be called angle 1. Those are the 4 acceptable names from here. What do we notice about the middle letter? It's going to be the vertex of the angle themselves here too. By looking at a name too, also by looking at a name, you're able to determine some other things here too. So remember, the vertex is the common endpoint of a ray, right? Common endpoint of a ray. So what we see here, we see one of the rays here is ray AP here. So if I knew that I had an angle TAP, I would know that one of my sides, okay, side of the angle would have to be ray AP, because look at this. This is why the vertex is important to be in the middle of this, also for classifying it, but also we get some information from it, is that we're able to tell that A is the vertex, so that's a common endpoint of a ray, so that means ray AP is one of the rays, and then the other ray is actually ray AT. Okay, ray AT is the other side. And we can get that because this is a vertex, so it's a common endpoint of a ray. So AT is the other side, just by reading that right here. Side AT is what we get here, okay? Side AT or ray AT and ray AP. So it doesn't matter. So the important thing is vertex is in the middle, and then the 2 points that are on the sides that are indicated in order to write what the rays are, those go on both sides of the vertex, and you're good to go here. Okay, so this one is kind of important here. You're allowed to name this angle A. Reason is, well, where do you get the A from? The A is the vertex, of course. Okay, we're allowed to name it by its vertex without the other letters here. The reason for that is that there are no other angles shown that use A as a vertex in the diagram. Okay, so of course, any point I could draw on, for instance, I could draw on another angle here that uses A as, right? This is another angle here. Let's make this PAX right here. If I drew another angle here in this diagram, I could call this angle PAX. I could name it that, but I can't name it angle A, right? Angle A. I can't name that angle A. Why can't I name that? At that point, I wouldn't be able to name this angle here, angle A. The reason is because I have more than one angle where this is using this as a vertex, okay? So you're only going to use the naming of the vertex as naming the angle if there's only one angle shown at that vertex right here. So let's go ahead and get rid of the part in purple so that it doesn't confuse you right here. And we'll get back to that in a second and let you practice it. But you can only name an angle by its vertex if it's the only angle shown in that diagram. And again, of course, there are infinitely many angles you could draw starting. And say you have a point right here, right? We can have an angle at this point that looks like this, that looks like that, right? That looks downward like this. And you got yourself an angle there. But if you're only showing one in the diagram, you can name it by the vertex here. Okay. Finally, we have here angle 1, right? And this is just something to look out for when you're doing this, is that you can also name by the number that appears here. So this is just labeling it that this is angle 1, and you're totally allowed to do that. If it doesn't have a number there, you can give it a number and name it something. Okay, so here's exercise number 1. We can just do them together. Let's make this angle 3 because we've already talked about angle 1 here, angle 2 here. This can be called angle 3. It can be called angle. What's another one character that I can put down? I can name it angle R. Sure, there's only one angle there. And finally, we have angle ARP, and we have angle PRA. And we got the 4 names of the angles right here. Okay, this one here, a little bit more complicated here. It's pointing to this angle that we have in the diagram here. This is going to be angle 1. Okay, angle 1. Maybe start with the letter. Can I do another single digit? Well, let's get back to that in a second. Let's first name it here. L. I'm going to put that in the middle, and then I'm going to mention our rays. We have ray LI, okay, that's one of the sides. And finally, we have ray LO. Look at that. So now I can name this. This is angle ILO. Next one, angle OLI. That's another thing I can name this. Can I name this, guys? Can I name this angle L? Am I allowed to do that? No, I can't name an angle L. In fact, you can't name a single angle in this diagram angle L because there's more than one angle using point L as its vertex, right? As vertex. So another thing to point out here is that what a lot of people think here is that the one that we just did, and I'll leave that in green here, was angle ILO, which is right here. Okay, we have that as an angle. We name that angle ILO. Some people think that, you know what, I can name this one. What if I just named this one by what I named it? So this can be angle 2, or it can be angle OLN. And so that indicates what the rays are here. Well, couldn't I just name this angle here angle L, right? Isn't that the larger angle formed of the 2 angles here? Because notice here, this diagram is a little bit confusing, and we'll get into this more. I think I explained this better last night too. But this diagram here, we see one angle here, we see two angles here, but wait a second, there's a third angle, right? It formed this here is ray LI and ray LN, right? So they have a common endpoint at L. So this would fit the definition of an angle here. So this angle plus that angle actually looks like this would form a third angle right here, okay? Can we call it angle L? No, we can't. No, we can't. So again, this isn't angle L right here. This is angle ILN. Okay, so that trips people up. So be aware of that, and you'll get practice with that. I'm not going to spend any more time on it here. Okay, so getting down to part two, we got measurement of angles here. So this is what we're talking about. I think you all know how angles get measured. This is called a protractor, okay, a protractor. And I'm going to tell you a bit about the angles measures and what it can be between, okay, because it's between something here. But I want to point this out that an angle gets described by its measure. So this is kind of like segments, okay? Segments exist. Segments are the shape, right? Segments are the shape. So we draw a shape, okay, like this is here. What would we say about this shape here? AB, okay? What would we call it? We would call it segment AB, okay, segment AB. So you'd have to draw it like this. What if we knew that, say this were 3 centimeters, for instance, saying that this is 3 centimeters, this here is 3 centimeters? Are we going to say that segment AB is 3 centimeters? No, we would say that distance AB. Oops, sorry, that was a big mistake right there. I'm going to get rid of that. Distance AB equaled 3 centimeters here. Okay, so remember that segments, this is segment right here, this means distance, or it means length, okay, distance right here. So segments get measured by distance, angles get measured by their degree measurement here. So if you just think to actual angles, right? Angles are made up of two rays, right? Rays continue infinitely, that share a common endpoint. So what every angle has in common is that it's made up of a ray and another ray and has a common endpoint, and it goes forever, right? Goes forever. So if you're comparing angles, right? If you're comparing angles, what's the difference between angles here? If I have an angle like this that goes forever, or angles like that that goes forever, or an angle like that that goes forever. Picture that these are being rays here. The difference in rays are the amount of hinge it has. I like saying hinge, right? Where do I get hinge from? A hinge is like a door hinge, right? Opening a door, opening it very wide or opening it very close to the front creates a small angle or a very large angle here, okay? So that hinge that an angle has a particular measurement. This is a bigger hinge, and therefore will have a bigger measurement. There we go. This is a much smaller, right, hinge, and we'll have a much smaller measurement. Anyways, you guys have done protractors before, so I'm hoping you get that. The big thing is here, you got to use this notation, okay? The notation M angle TAP means measure of angle TAP in degrees. Okay? So this is sort of similar to this, where you never say AB equal to 3 centimeters. That's false because this is true up here. So that's false. You never say that. Just like that, you would never say this. Angle TAP never equals anything else, right? Never equals anything. Because angle TAP is just an angle. The rays go forever. What's different about angles is that they have measurements. They are measured in degrees here. So you need this. You need this front part here. That needs to be written if you're talking about a particular measurement here. Okay, so if we dropped this, right, measure of angle TAP, if you had a protractor, you might get a little bit more closely, but I'm trusting you guys have done protractors in middle school and can kind of eyeball this pretty well. So this looks like this. I would say maybe like is about 40 degrees or so. Okay, about 40 degrees. So measure of angle TAP equals 40 degrees, okay? And that's how you'd write the actual angle measurement in degrees, okay? Measure of angle TAP in degrees equals 40, okay? So you gotta do that. You're never gonna see angle TAP equal to 40. Not gonna have that, okay? So another thing we get here, measure of an angle is between 0 and 180 inclusive. I'll get to that because that's actually a rule, right? A rule we'll get to, okay? So take a second, actually, let's just practice using a protractor. Remember reading it here. This is a 45 degree angle, looks like, so it looks, it goes up here, 10, 20, 30, 40, 50, goes up all the way up to 180. Still, this one here, if you want to measure, say, this angle, boom and boom, maybe you'd use the red setting here, because here, this is 0, that's 40, that looks like it's about 40 degrees. So take a second, just practice this, because it might be a little while. Tell me these angle measurements. And can you get all of them, actually? Are you allowed to put a number next to all these here? Or have I intentionally misled you? Take 45 seconds, I'm going to do them as well. Ready, set, go. Check your answers afterwards. All right, and now I'm going to pause here, okay? This is pretty easy. The first two are pretty easy. So measure of WOZ, that one's here, right? This is WOZ, and this is pretty easy here, okay? So where's this one pointed at? It's pointed at 0 degrees. This one's pointed at 45 degrees, so this has got to be a 45-degree angle right here, okay? That's pretty good. This one's also pointed at the red 0 degrees. This one's pointing at the red 135 degrees. That means this is 135 degrees. We're going to come up with a formula for a second to actually figure this out when it's like, say, for instance, this angle. We'll talk about this next. Okay, angle O, measure of angle O. Ooh, interesting. I see O there. That sure, it's a vertex, okay? Sometimes you're able to name angles by their vertex, right? So here, right, this is angle R would have a measurement here. Does angle O have a measurement here in this diagram? Well, just like the other one, there are an infinite amount of angles that could be used with this as the vertex. But wait, what we see here, we see at least 3. In fact, we see like more like 7 angles here that are using vertex O as its vertex, or point O as its vertex here. So we actually can't answer this. So hopefully you put no there. Okay, that was supposed to trick you up, and that's definitely something that I'll see from you guys here. You'll be telling me about what angle O, and I'll have to be like not specific enough. That's what I'll say. That's not angle O. Anyways, angle YOW, can we say the measurement of that here? Are we allowed to? No, we are missing something right here. What are we missing? Okay, angle YOW, sure, I can identify that. This is angle YOW. That's right here. But if you're saying angle YOW, what are you talking about? You're talking about the shape. Okay, so my answer here, angle YOW, I'll be like, well, that's 2 rays. I know that. That meet at a common endpoint. What do you need to say instead? Well, you need to talk about its measurement. So that's the thing that when we're talking about numbers, right? That's the nice thing about angle measurements, gets numbers into our math problems. You need to be talking about the measurement. So here, this was missing the M in front. If it had the M in front, you can answer it. If it doesn't, then it's a trick question. Okay. So measure an angle YOW. Let's get that angle measurement here. And that's this last part. Measure of one angle, other angle not mentioned here. Let's just do this one here. So YOW. Okay, so this is a little bit harder. Let's think about how we would do stuff like this here. This here looks like OY is pointed to 40 degrees, and it looks like OW is pointed at 135 degrees, the way that I'm reading it. I'm reading the reds here. Okay, so the question, what is this whole measurement then? As we go from here to here, right, how many degrees is that? How much hinge is that here? You're probably pretty able to do this pretty quickly in your head, but our answer here is 95 degrees. Okay, you're going to see a formula in a second. I'm going to give you a formula here. But the idea is if one ray is pointing this on the protractor, another ray is pointing that in the protractor, what you can do is you can subtract the two. So I can do 40 minus 135, and that should give me my answer, right? Because it's just the difference in the values on the protractor that tells us how big that angle is. Well, what's the problem with this? This would actually be negative 95 here. So what you have to do is drop the absolute value. Get a lot of absolute value practice in these first few sections here. But anyways, the nicest thing about geometry is that almost all of your numbers this year are going to be positive. Why? Because measurements, the way we measure the Earth is positive. We're talking about distance. We're talking about a positive distance. Distance is always positive. Same thing with us here with angles. For us here in geometry, it's different in other maths, but for us here in geometry, angles will always be positive here. So if I knew that this were, say, x, and I knew that were y, I would just have to subtract x and take away y. And then if I take the absolute value of that, that's going to tell me that the angle measurement here was 95 degrees, because the amount of degrees in an angle is always positive here. So if you're getting that through subtraction as negative, just make it positive and you're good to go. Okie dokie, moving on here. We got a new rule. This one is not an important one, so don't spend that much time reading this being like, what the heck is this talking about? Because this is something, this rule here, right? Underline that, not an important one. This will be an important rule for later when we are adding angles to diagrams. This will be some justification why we're allowed to do that, so you're not going to have to worry about this one quite yet. It's called the protractor postulate. A lot of words written right here. Okay, a lot of words written right here, but we got the takeaways down here. We'll talk about the takeaways here. My file got kind of messed up, but this space here is not for anything here. So, anyways, read this on your own time. I'm probably just going to take away take you through the takeaways so you understand what the ruler postulate tells us, and then we're going to move on because it's not that important one. First thing that I want to remind you guys of, though, is again, what is a postulate? A postulate is an assumption that's so obvious, right, that we can all agree to, that we accept it as a rule. Can it be proven? No, it can't be proven. That might be kind of hard to understand because we haven't gotten to proofs yet and proving facts. But this is a postulate, okay? So what a postulate basically is, the thing that makes it different than a definition. Remember, a definition tells us what something is, right? The definition of an angle is that it has two rays and it has a common endpoint. That's what an angle is. What a postulate is something more complicated than that, in that these are sort of things about angles that, you know what, about angles, angle we haven't defined already, but about an angle, let's agree to what an angle does, what we're allowed to say about angles here, because it's so obvious what they do. We can't prove that angles operate this way, but it's sort of humans coming together being like, this is what we're going to agree to, kind of about angles here. The first agreement in the ruler postulate is this, that if we have OA and it's paired with, so we again made up of two rays. Maybe I'll sketch this out for you guys real quick. So if we have an angle, a ray OA, okay, ray O, ray right here, and it's paired with 0 degrees on the protractor itself, and then we have another ray. We have OB, and that is paired with, and they are opposite rays here, okay? And this looks like this here, and it's paired with 180 degrees, this here. And if we have this, and we have this special type of an angle right here, it's going to be equal to 180 degrees. That's basically tell us that in this first statement here that an angle like this that I've drawn like this, it has 180 degrees of measurement. Okay, so the first kind of assumption that they're trying to get across to us here is that larger angles are closer to 180 degrees here. If I draw the largest angle possible, this is sort of saying here, if I have OA and OB and we're pairing it this way, this is the largest angle possible. This is the way we can get two rays pointing opposite directions. We will count this as 180 degrees. Okay, so larger angles are closer to 180, smaller angles are closer to 0 degrees. I'm going to get back to that a little bit later, that idea, okay? Second thing, what the ruler postulate allows us, telling us, is that we're allowed to, if we have different angles within this or different rays within this, here's a formula for us to calculate what we would measure this angle here, okay? So if we have an angle that's on the protractor, so for instance, OP is another ray, okay, and say that's pointed at like 30 degrees on the protractor right here. Here's OP, and we have OQ, that's another ray, okay, and that's pointed at, say, we're looking back to the protractor up here, for instance, maybe pointed at like 120 degrees on the protractor right here. The way that you solve for this is that you take the absolute value of the difference of the two places that these rays are pointing, and that will tell you your answer. This one's easy because it's positive already, so it remains as positive 90 here, okay? So this is just a formula right here. And the reason why they do it this way is because, well, if we didn't know it's 120, it's just like this is pointing towards X on the protractor, and this is an unknown place that this ray is pointing here. What you just have to do is take the absolute value of X minus Y, and that would tell you what the angle measures, right? Sort of a formula to use. So anyways, the protractor here, protractor postulate, that's just a formula to get the measure of an angle here, okay? I'm definitely going through this a lot faster than I went through last night. I feel like it's not going quite as well as it was last night. I'm frustrated by that, but hey, let's just try to get through it and go through. Okay, protractor postulate, not super important, just tells us that any angle measurement is between 180 degrees. Larger ones are at 180, like the largest is 180, and then smaller ones are less than that, and up to 0 degrees here. And then it's a little formula for solving for it when we're using a protractor. Anyways, let's get to some definitions. These are more definitions. These are names of different types of angles. Okay, so we figured out how to name an angle, and I took you through that. Now we're going to go through the 4 classifications of an angle here. Okay, so I told you a second ago. Okay, that this is The largest angle we have, 180 degrees, that's going to get a special name to it. So I got to say, when I took geometry the first time, I'd never heard of what a 180-degree angle was. And also, I thought to myself, isn't a 180-degree angle just a straight line? We'll get back to that in a second. One thing I wanted to point out here too is that perhaps you noticed this, that when I did the 120-degree angle, subtracted from a 30-degree angle, this here angle, right, measure of angle PO, and I didn't put the point here, but the point here was supposed to be Q. Okay, measurement angle POQ actually happens to equal 90 degrees. Okay, 90 degrees. You may have heard of this before, but a 90-degree angle has a special type of an angle. In fact, you see this symbol for 90-degree angles right here. Anybody know what that symbol means? That means a symbol for a right angle. So that's what I want to begin with down here, is that according to the hinge, right, according to how open an angle is or shut an angle is, and remember, an angle can't be totally shut. I'll get back to that in a second. But the more it's open, right, obviously the bigger it is, and we can classify based on how much hinge there is. This has a different name than this, and this has a different name than that, okay? And we'll talk about all four, okay? So the thing that you probably got here is that a 90-degree angle is a right angle. A right angle, okay? So a right angle is the first thing that we'll classify down here. And a right angle is a classify, well, it's an angle that measures what? Measures exactly 90 degrees. Exactly 90, okay? And that is a right angle. So here, right, with a 90-degree angle, it's gonna end up looking like this. So if this whole thing is 180 degrees, right, we have a point here, we have another ray pointed out here, right? Say if we have another ray here, then technically this whole thing, right, would be 180 degrees, okay? But if we have halfway in between that, this is obviously 90 degrees, and this is something called a right angle because it's upright, right? It's upright. That's what they mean by that. We'll spend some time talking about right angles, but when we're talking about upright, we're talking about going straight up, right? If this is on the horizon, straight up, we can think of a right angle. So as your floor hits the wall, that is a right angle. That is a right angle here, okay? Other names for angles is if we have kind of the same diagram, right? If I have my ray here, and this is the largest angle I can create, right? This is the vertex here. So notice here, this is a ray that direction, vertex. An opposite ray here would be 180-degree angle. So you'd have two rays, right? A ray here, a second ray, a common endpoint. That's 100 degrees. So 90 degrees, if we're less than that, right? Less than 90 degrees here, that has a special name. It's a smaller angle. What do we call smaller angles here? Well, we call them acute angles, right? Acute angles. So that's how you're gonna remember that. Acute, right? What's the word acute means? Acute, big or small? No, acute is kind of small here. Okay. So an acute angle is an angle that measures between. Well, it's smaller than a right angle, so it's not up to 90 degrees, but it's also bigger than 0 degrees. Okay. So between 0 and 90 degrees is what an acute angle is here. Here's a trick question, right? Here's something that somebody might ask you here is can you draw a 0-degree angle? Okay, does a 0-degree angle exist? Is that possible? Okay, well, you might think here, well, you know what? If this is 0 degrees, this is 40 degrees. Okay, this would represent an acute angle. Okay, this would fit the definition of being acute. But then the question is a 0-degree angle, does it exist? And if so, is it acute? Isn't acute? Well, it's not acute here. I'll get to that later, but doesn't exist. I just wanted to point this out that a 0-degree angle can exist here. Okay, so if this is pointing towards 0, what a 0-degree angle, the claim of that would try and be showing us here is that you'd have a ray, we'll make this OA, okay, pointed this way. And you might say, you know what? If we have two rays meeting at a common endpoint, isn't that an angle? And if I draw this on top of OA, okay, and I say that that's P right here, would this be angle POA? Angle POA. The answer is no, it's not angle POA. The reason is the very first section, the very first class you had here, is that when you say two rays, okay, when we say two rays right here, we mean two distinct rays, okay? In your book, if they say two lines, they mean two distinct lines. Three planes, they mean three distinct planes here. So the reason I call that out is because, again, in other maths, if you have things overlapping, you can count them as more than one thing. In geometry, if things are overlapping, we would just call that one thing. We would call this one ray. So here, a 0-degree angle does not exist. So that's why we see a less than symbol here, is because in order to be an acute angle, the angle itself, its measurement needs to be larger than 0, but less than 90. less than 90, okay? So anyways, I also wanted to point this out here because I talked about this the last section, and that is that I have this double arrow here. And this is sort of getting us to think about how we can kind of abbreviate things like definitions, okay? So later on, you guys are going to see a postulate. There's a single-headed arrow right here. This means an if-then. Okay, I'll get back to that later. An if-then statement. This is something called an if and only if statement. If and only if. So this is how I'm going to hopefully abbreviate this, and you can abbreviate this in your notes here, okay? So say, for instance, angle A is an acute angle, right? That's given to us, right? We know that angle A is an acute angle. Angle A is an acute angle if and only if it measures between 0 and 90 degrees. That's how we can read that. So by knowing that A is an acute angle, we would know this fact. This fact is proven for us. It's part of the definition, okay? Also here, the reason why this is a double-headed arrow is that if we knew something is an acute angle, that would tell us that this is true, right? And the definition of acute says that it measures between 0 and 90. If we knew that we had an angle, say we came across it and it's a 60-degree angle, okay? We could then get to justifying what? We can go the other way here, boom, and establish that it's acute by definition, okay? So when I write definitions out here, I include a double-headed arrow, and this will become important later because knowing this fact here is enough to conclude that fact, or vice versa, okay? So as we get more practice with that, I think that'll make a little more sense why I'm doing it this way, but wanted to point it out now in case you're confused why or wanted to hear more. Okay, so if I knew an angle were a right angle right here, okay? If I knew I had an angle and this were 90 degrees, okay, then I would be able to conclude that this was a right angle. Okay, a right angle here. And so reminders on that, this symbol, when we see it in diagrams, you are allowed to conclude that it is a right angle here, okay, if we see that symbol. So the reason why it's like the symbol is because it creates kind of a little square at the bottom here, right? Because this is 90 degrees and, right, these are the same width as it is height. This is 90 degrees. It's sort of like another right angle here to indicate that this is a special angle right here. It forms exactly 90 degrees. We got a little square down here. So this is a 90 degree angle. Okay, going a bit faster here because again, I want to get through all the stuff. You don't want to sit through all this. I don't blame you, but again, I do want to have these teacher explanations available because, right, it might be a little hard with what you can do all the stuff if you're just reading it on your own. Next word, obtuse. Okay, so again, we're getting bigger. We're getting bigger. So let's draw in an obtuse angle. We got this is going towards 0 degrees, 90 degrees. Okay, we've already talked about the acute angles. I'm not going to draw that in. Well, I could draw it in. That's acute. This here is something special. It's the largest angle we have. So this, right? This here is an obtuse angle, okay? An obtuse angle is an angle that measures between 90 and 180, okay? So an obtuse angle, is it also a right angle? No, it's not. That's why we have the less than symbol here. So 90 is less than the measure of an obtuse angle. So to become obtuse, you go beyond a right angle. Right? Obtuse. Why are you so obtuse? So obtuse is actually kind of an adjective. Why are you being so obtuse? So it's kind of off, right? Set off, kind of big, right? Like outside of it. Obtuse, we can kind of think of that as being kind of a big angle. Not the biggest, but big, okay? Because we do get a final one here. So notice here, an obtuse angle isn't going to be form a perfect straight line here. So this is obtuse, but that down there, not going to be obtuse. That gets another angle, and it's called a straight angle, okay? Make sure you know this because I actually didn't know this going into geometry, that straight angles exist. This here is going to be your straight angle. Start with the ray, points towards 0 degrees, or it could point like to different degrees on the protractor, but 180 degrees beyond. That's going to be what a straight angle is here, okay? So it's not acute, it's not right, it's not obtuse, it's the final situation. It's this, the final countdown. Boom, okay? So just to reiterate here, this here is a straight angle. I'll make it angle A because we're talking about angle A's here. I'll make this ray AB. I'll make this ray AC. And here, the measure of angle BAC is 180 degrees. Okay, measure of angle or C, I could make it CAB as well. I'll do BAC here, so that's what I said first, equals 180 degrees. Therefore, we can establish that angle BAC is a straight angle. Okay, so a straight line, you can identify angles there. The reason is, again, just to remind you the reasons here, is that If we started with a straight line, let's maybe do a different diagram right here. What can we identify on a straight line? Remember, a line is made up of an infinite number of points. So if I put a dot right here, that forms what? It forms two opposite what? Two opposite rays here. So here, by indicating that this is a point on here, I have a ray here, I have a ray here, and they're both meeting where? At a common endpoint. So what we have here is a ray going this way, ray going that way, meeting at a common endpoint, and therefore that fits the definition of an angle, okay? So a straight line, if we drop some points on there, we got an angle. So we can call this angle A if I want to. If I put some points down, I can call it other stuff. I can call it XAY, for instance, okay? So this goes the same thing here too. If we're told something is a straight angle, then we can make the conclusion that that angle measures 80 degrees. If we've somehow proven or it comes up, like we see something measures 180 degrees, we can then make the conclusion that that it's a straight angle. We can go that direction too, okay? So I wanted to point that out. All right, another rule. This one's important, okay? So it was important you know these four. That's why I spent time on it. It's important you know how you name angles and what an angle is. Less important what the protractor postulate is. So that's why I don't really mind that explanation didn't go so well. This is an important rule, okay? This is an important rule. So this is something called the angle addition postulate. Before we get into this here, right, angle addition postulate probably looks familiar to a postulate that you had in section 1-2, okay? Do you guys remember that rule? You had one rule that I said wasn't that important called the ruler postulate. What was the other? You're going to have to kind of memorize these postulates and know that they exist, okay, in order to use this stuff in the future. What was the other postulate? Yeah, the other postulate was called the segment addition postulate, okay? So go back and review that if you just like, what is that? I don't really know this. Go back and review the segment addition postulate. Remember, the segment addition postulate was a thing where if you have a segment, you can add parts of the segment, lengths, parts of the distance of the lengths of the segment together to equal the whole length of the segment here. Okay, so let's just remind you what the segment postulate is here. So say if I have a segment AB, segment AB here. In order to one method you could have to determine the length of AB. Well, what if you knew what distance AX equals here? AX. Okay, and you knew what distance XB equaled here. Notice here, X isn't a midpoint. I drew that intentionally. It doesn't have to be a midpoint to be true. X is just between A and B here, okay? So what the segment addition postulate tells us is that you can take a part of this segment, find its distance, a part of it, and add the other part. Part plus other part equals whole. That's how I get you to remember the segment addition postulate here. And it's how I'm going to get you to remember the angle addition postulate in a second. Part plus this part right here is going to equal the whole length, okay? I know you think that's pretty obvious. You're just like, well, why isn't that just a fact that we know? It kind of is, right? This is innate. So postulates, again, are rules, okay? And they're so basic and obvious. There's something that we can all agree to here. So obviously, right, if this were 3 right here and that were 8, what's the conclusion we can make? Oh, it's got to be 8, okay? But the question is, how could you prove that, right? How could you really be sure 3 plus 8 here is going to give us the whole length? Well, we need to agree. This is super obvious. If you have a segment that's collinear with another segment right next to it, just add the two together and you got the whole segment. Okay, so it's just something that needs to be established as a rule that we're all allowed to do because it's so incredibly obvious. It's got to work that way. Okay, so that's sort of this postulate here. This is going to be the same thing here. So I'm not even really going to read this one, but I want you to get the idea that this is part plus part equals whole. Okay, so for this one here, if I knew that this was 30 degrees and this was 15 degrees, I can take to get measure of angle AOC, Miss Ocasio-Cortez right there, I can follow this postulate here. If I see this like here, I got angles next to one another, I can take the part of it, which is measure of angle BOA, and add to it the measure of the angle that's right next to it, which is measure of angle COB, and that's going to give me the larger angle right here. Okay, so once again, this is a part plus part equals whole assumption kind of rule right here, okay? So now I can just add together. If I wanted to get this question mark, I'm allowed to just add the two together. Seems obvious, and it is kind of obvious, but now you have it here, okay? The important thing is that you need to understand what this means. what they're doing here. So when you see something like this, it's oftentimes they're talking about the angle addition postulate, the angle addition postulate. Okay, so this rule comes into place when your angles are something called adjacent to one another. I'm going to define adjacent for you later. But again, just to recap, right, you take this angle, and what does this angle share with the angle right next to it? It shares a side. Okay, so when you have an angle with a common side and they're coplanar, that is something I'll get to later, you can just add the measurement of this angle and add the measurement of that angle, and that gives you the measurement of the whole thing, okay? Seems obvious? I think so. I think so too, okay? So this angle plus that angle will give you the whole angle right here, okay? So this is sort of what you're being look out for, and we'll get to this in diagrams down here in a second, okay? Second part, there's actually two parts of the angle addition postulate. I call this angle addition postulate 1 and angle addition postulate 2, okay? And angle addition postulate 2 has to do with straight angles, okay? Straight angles. Okay, straight angles, which we have here. Okay, so this is the same thing here too. So this is just saying our if then, right? So that's another thing to notice here, that postulates are often written as if then statements. If I know this, then so if I know this, remember the if is called the hypothesis again. If I know this, then I can make this conclusion. Okay, what was the conclusion we made in the first one? If I know this, I have a ray, and this ray is being shared between these two angles here. I can add these two together, and my conclusion is I add the two together, it gives me the sum of the whole. This is the same thing too, where I have a situation, but you know what? AOC is a straight angle here. This fits the definition of a straight angle because we have ray OC and ray OA, and they share that common endpoint of O here, okay? So in this situation here, we can take measure of angle BOC, again, part plus part, measure of angle BOA, equal to the whole. Okay, so here's the conclusion we make, equal to the whole. So I could write this. I'm more than willing to write this following this rule up here. I can write measure of angle AOC. Okay, I can do that. But this second part is actually saying, we can say one more thing than that. Because what do we know about measure of angle AOC? Well, it equals 180 because it's a straight angle here, okay? So your conclusion you're able to make here isn't just that measure of angle BOC plus measure of angle BOA equals measure of angle AOC. It's that it equals 180, okay, equals 180. That's the one difference here, okay? So this is a way to get the number 180 into your problems, right? Sometimes you want to get numbers of problems, and it's an important thing, okay? So anyways, let's, I know I'm going through this fast, right? There's just a lot of stuff in this section. So let's quickly fill in kind of what we can conclude, our takeaways here, what can we conclude. So if I have a diagram that looks like this, okay, what can I conclude about this diagram, right? Remember, angle addition postulate. So we're practicing the angle addition postulate here. And that is part plus part equals whole. So what I can conclude is this, is that measure of angle XYW plus measure of angle WYZ equals measure of angle XYZ. Okay, that's what I can conclude. And with that, because these are actually have measurements here, I could substitute in, right? So I'm using the angle addition postulate to substitute in. So I can do 30 degrees plus another 30 degrees is going to equal, well, 60 degrees, okay? So you can use angle addition postulate to prove that this actually is a 60-degree angle, right? XYZ has got to be 60 degrees. Looks like common sense. It is common sense, but it has and it's just an agreement. This is how we're going to solve problems like this in the future, okay? Looking at this one here, okay? So this is the first takeaway. Let's just practice using this one. Let's not talk about the straight angle yet. So not talking about straight angle here. So what's this here? What's one way I can use this? If I have this diagram right here, it's going to fit the if statement here. So remember, with these single-headed arrows here, the left side is the if, and the right side is the then, okay? If we have this as a diagram, right? This is our hypothesis in situation. We have a diagram for us here. What can we conclude? If this is our diagram, then we can conclude what? Well, one conclusion we can make, for instance, maybe talk about this angle. What's one thing we conclude about that angle right there? Well, the measure of that angle, and that angle is what? SAL. That's going to equal what? The sum of this guy right here and this guy right here. So measure of angle 2 plus measure of angle 3 and that here. So this is a fact that we could prove because we're following a rule, right? We're following a rule. The postulate's the rule that helps us establish that in this diagram here, measure of angle 2 plus measure of angle 3, got to equal measure of angle SAA. Okay, let's practice number 2 here. These are straight angles right here, straight angles right here. So when you have straight angles, you can say stuff about straight angles here. SAT is our straight angle in this one, so I want to say, what's the conclusion we can make about measure of angle SAT? I put SAL, I meant to put SAT. Measure of angle SAT, what does it equal? Okay, well, what we got to do is the angle addition postulate's written for the sum of two angles. Okay, that's kind of annoying, and your book will reiterate that a little bit later. So first thing we need to do, we need to find two angles that add up, that add up to that straight angle here. So let's use this one. Let's use measure of angle KAT plus what has got to equal measure of angle SAT. Well, that would be measure of angle 3. Okay, so measure of angle KAT plus measure of angle 3, right? The sides, this angle here and this angle here share a side, right? So when you're sharing a side in the same plane, you can add those two angles together. I'm going to tell you the measure of the whole thing. So if we're sharing a side here, then this ray that's not shared and this ray that's not shared forms kind of a straight line. So it forms a straight angle here. So we can make this as our conclusion. But wait a second, what's something else I can conclude? Something that's better than this. I'm actually going to erase this thing here. Because what did we actually prove numerically about the measure of this angle plus the measure of that angle? Well, since it adds to be a straight angle, it equals 180. Okay, so just wanted to point that out here. This is AAP2, right? The second angle addition postulate, that an angle, two angles added together, if they form a straight angle, we can conclude that they add to 180 degrees. An assumption, a rule, you might be like, why is that important? It'll be important later. I'm glad you're watching this video. Okay, let's try to wrap this up here, guys, because again, it's the second time I'm filming this, and it's not going quite as well as it was the first time. So not as fun when I have to do this twice. But anyways, hopefully you're at least getting stuff dumped on you. You kind of understand, hey, this is maybe how I'm going to start thinking about it. Do my exit ticket later, do my problems, and hopefully I feel like I'm feeling okay about this stuff here. Geometry does get better too. It's just a lot of information right now. Anyways, we're almost there. 3 more definitions. Here, we talked about what congruent segments were last section. Boom and boom. Congruent segments are, let's say that AL equals 3 and BC equals 3. Then we can make the conclusion that segment AL was congruent to segment BC because they have the same length. And remember, congruent segments get this symbol too, right? Say that these are both 3 centimeters. That would be the definition of congruent segments. We're also going to have congruent angles, okay? Congruent angles are not segments anymore this time, right? We're talking about angles. We'll classify them as angles that have well, these are congruent angles because, right, AL equals BC, okay? If AL equals BC, then we can make the conclusion that segment AL is congruent to segment BC. Let me say that and rephrase that because I think it's a little bit confusing. AL, when we write AL like this, we mean distance AL or length of AL. Length of AL is 3. Length of BL equals 3. If segments have the same length, then they are congruent by definition. That's the definition of congruent segments, are segments that have the same length. What about angles? What would make angles be congruent to one another? So congruent, right? In congruent geometry just means kind of exactly the same, right? Things that are exactly the same as to one another. So for segments, we talk about segments in terms of their length or their distance. In angles, what's going to make, because these angles that I'm drawing right here look pretty darn similar, okay? Look pretty darn similar. What's going to make them be exactly the same? Is it going to be the rays, right? Going to be the rays? No, rays are the same in all angles because rays go on forever. They all meet at a vertex, right, and go on forever. So the rays we're not thinking of, what are we thinking about? We're thinking about how we measure them. So if this were, say, 30-degree angle, and this were a 30-degree angle right here, their measurements equals the same, then, okay, I'm going to do that single-sided arrow for us right now. Remember, single-sided arrow means if we know this, then we can conclude something. Then what we can conclude is that these two angles are congruent to one another. So before I finish this out, this example out here, I'll just try to redraw them over here. Congruent angles, and here we have the congruent symbol, and then we have angles, right, for angles plural, are angles that have the same measurements. Okay, If I have two angles that have the same measurement, then I refer to them as congruent angles, okay? Here is the symbol to mark congruent angles. We have boom, that symbol right there, and boom, that symbol right there. So that's how I'm labeling congruent, the way that I do it, okay? So this means congruent, okay? This means congruent here, congruent angles, okay? And so this, if I said this is an if and only if statement, measure of angle DAF equals the measure of angle GAH if and only if those are two congruent angles, right? So if we know we had congruent angles, the conclusion we can make is that they have the same measure. But if we know we have two angles that have the same measure, the conclusion that we can make this way is that they are congruent angles here. The definition of congruent angles, okay? If you have more than one angle in a diagram, you might see more than one tick mark. So I just wanted to point that out. The tick marks correspond to whether or not they're congruent or not. Okay, I'm going to keep moving on. I go on for days with this stuff here. All right, you need to know about adjacent angles because I kind of mentioned adjacent earlier in this lesson, and they're pretty important. These are not adjacent angles up here because adjacent, the word adjacent, what that just sort of means, you should know what the word adjacent means, right, from English class or just to talk to people. Adjacent means immediately next to something, right? I am adjacent to this thing here. So picture a classroom. Pretend we're in a classroom right now. I get a phone call from Mr. Beltran, right, the assistant principal. He says, what room are you in? I was like, I don't know the room number. And he's like, well, what is the name of the teacher in the room adjacent to yours? If he says that. So the adjacent classroom to mine, I'm not going to say across the hall, right? I'm not going to say across the hall. I'm going to say the room right next to mine, the one that shares a wall, right? Room that shares a wall, okay? So for adjacent angles, you can think of adjacent angles as angles that don't share a wall, but kind of share a wall. They share a side, okay? Share a side. So adjacent angles are angles that are, we also have a co here, okay? Co here. And the co thing here is they're obviously not collinear, right? Because we have points all over the place, but they're coplanar. Okay, coplanar. The reason why I call that out is because you use the angle addition postulate when you have adjacent angles, and that's only when your angles are, use some different fingers here. I'll maybe use 3. When your angles are coplanar here. Okay, so picture I have an angle right here. I have another angle right here. These would be adjacent angles if they are coplanar, okay, because they share a side. Okay, this middle finger here would be the side in this angle and also in this angle right here, but they're also coplanar, okay, coplanar. I'm trying to make them nice and flat in a surface here, okay? If I twisted this, right, if I twisted my fingers a little bit and took up some more space, let me show the camera like this here. These are now not coplanar. They're taking up space. So coplanar in one plane, and I can rotate that plane, that's fine. But if I rotate it this here, then the angle addition postulate's not going to work, and we're not coplanar, so we're not adjacent. Okay, so all of these are all coplanar because we're writing this on a piece of paper, but in 3 dimensions, right? If they share a side of an angle, if they're the two other rays that don't share the side are not coplanar, then it's not adjacent. Anyways, it's kind of confusing. I'm sorry about that. It's not that important. Anyways, they have a common endpoint, or not a common endpoint. We know common endpoints because of rays. They have a common side. Okay, there are angles that are coplanar, have a common side. And finally, they also have a common vertex and no interior points here. Okay, so let's take a look at this here to make sure we understand what this looks like here. Here are your adjacent angles. Okay, so here, common side, boom, common side's right here. Common side right here between these two angles. This one here on the right side is a little bit harder to see. We have angle 2 is right there, and then angle 1 is right here. Okay, so it has a common side and a common vertex, and they're coplanar. Here, angle 2, angle 1, common side, and it has a vertex right there that it shares between the two. Okay, angle 3 and angle 4 are not adjacent angles in these diagrams right here. What's wrong with this one? Why isn't this adjacent angles? Well, the angles aren't right next to one another. They don't share a common side. Okay, this one right here, these are not adjacent angles. This side here is part of that side here. Okay, so side 1 is different than this. Than side 2. Let me get it here. So this is angle 3 is right here. This is its side is right here. Angle 4, its side's right here. So the sides aren't exactly the same. They don't have a common endpoint. Okay, don't have a common common vertex. Okay, vertex is here. Vertex is here. And they are not adjacent angles, even though they kind of are sharing a side here. Okay, this one here, these are not adjacent, even though they share a side, right? Look, these angles here, angle 3 and angle 4 shares these two sides here, but the sides got to be in the middle, right? Got to be in the middle here. okay? Because can't be in the interior of angle 4. So none of the points in angle 3 can be in the interior of the angle 4. That's one thing that I mentioned the last time I filmed this video earlier on, which I really wish I did in this video, is that with an angle, okay, if this is a 40-degree angle, here's your interior of the angle, okay? Your exterior is over here. Okay, exterior is all the way around here. Interior is right in here. And then this is the angle itself. Because remember, an angle is just two rays, right? That's what an angle is. Two rays that form a common endpoint. Interior, exterior. Those aren't part of the shape themselves. Okay, finally, last one, bisector of an angle. Again, my form got all messed up, so I apologize for that. Bisector of an angle is similar to a bisector of a segment. Remember, a segment can get bisected, meaning that a segment can get bisected if something's going through the midpoint of the segment, thus creating two congruent segments here. Bisector of an angle is the same kind of thing where we get down here. A bisector is something that creates, boom, I'm putting the congruent symbols down so you get used to seeing them, that creates two congruent angles, okay? So then the question is, what is doing the bisecting right here? And your book defines it as a ray, okay? Bisector of an angle is a ray. So here, this here is the bisector of a ray. It could also get referred to as the angle bisector, okay? So bisector of an angle also gets called shorthand an angle bisector, okay? And what that is the ray that we could draw through. So originally angle XYZ was a 60-degree angle. There's one and only one ray, right? That's one of the reason why we're defining just for rays. There's one ray we can draw through point Y to bisect the angle, create two congruent angles right here, okay? So anyways, that's kind of like, we don't need to spend a lot of time on that. We can kind of move on and hopefully wrap this one up here, okay? So ray YW is the bisector of angle XYZ. Well, if we knew that YW bisected angle XYZ, then, right, we can conclude that, this is actually kind of interesting too. I'm gonna try to point this one out here. Look, YW, the bisector of an angle, is actually gonna include the vertex, okay? Actually include the vertex. Okay, and then this is going to be the endpoint of the bisector, right? The ray right here, okay? So using these letters, actually, I'm not going to look at this diagram, using these letters, if our bisector is YW, that means it's going to form an angle, which is angle WY and then Z here, right? WYZ. This angle here, right? This angle right here is going to share a side, right? It's going to share YZ with the larger angle right here. So WYZ is congruent to angle WYX, right? WYX. So that'll be something we'll be practicing, is just like looking at this information right here, making a conclusion without actually seeing a diagram like this, okay? So we know if we have a bisector of an angle, it's going to create two congruent angles from it, okay? And I'll leave it at that there. I think, I don't know how, especially because I didn't think this one as well as the last time I filmed this. Oh, we're like longer than I was last time I filmed this. Why the volume error? Why the volume error? Okay, anyways, let's see if we can wrap this up in like 3 minutes to kind of get you on your way. Again, I said you don't even have to watch this part of the video if you don't want to, but I think it's helpful to go through some of these examples because I'm going to call out some things that come up in your problem sets. This is definitely a longer video than last time I filmed this. Man, this is so frustrating. I hate doing these videos. I wish we could do this in class in like 25 minutes. Anyways, let's just go through them real quick because these appear like common sense problems, but you know they could be harder for some folks here. Find measure of angle KON. Well, here this would be something we'd use the angle addition postulate for here. Angle KON, that's going to equal right here, right? Well, 15 degrees plus 80 degrees, right? Because we know that measure angle KOL plus LON equals measure angle KON. So our answer here is 95 degrees. That's pretty easy. Let's just keep moving on here. You can also use angle addition postulate going to find a smaller angle here. Look at this one here. They want to get KOL. Look, that's a smaller angle. It's one of the two adjacent angles making up this large angle here, okay? So KON measures 118 degrees, and if I take away 102 degrees from it, okay, that's going to tell us this angle right here. Measure of angle KOL is going to equal 118 minus 102, which is going to equal 16 degrees. Okay, so we can use the angle addition postulate to subtract 2. Kind of confusing, that'll come up later in the future here, okay? Angle addition postulate here. Now we have some variables, okay? So when we have some variables, we're going to do the same thing, right? We're going to do angle addition postulate. We know that measure of angle KOL plus measure of angle LON would equal measure of angle KON, and it looks like we're given that, right? We're given measure of angle KON, oops, missed the M here too, as 120 degrees, and we're giving variables here. Look, we're given x plus 6 is KOL, okay, which is right here. So I can replace measure of angle KOL with its algebraic representation, x plus 6, and I'm going to add to it this algebraic representation, 4x plus 14, and now I've set up an equation that I can solve here. Look, this is measure of angle KOL, that's measure of angle LON, and they add together to be this whole thing. Part plus part equals whole, and that again is the angle addition postulate. So 4x plus, so now we just need to combine like terms, which if it's been a little while since Algebra 1, x plus 4x gives us 5x's, and 6 plus 14 is 20, and there we have it. Okay, there we have it, 120 here. So now we can solve this. 5x, we subtract 20 from both sides, we get 100, and now 5x equals 100 divides both sides by 5, gives us 20. Got our answer here. Okay, quickly rattling them off right here. We got measure of angle 6 equals 40, measure of angle 7. Well, that's got to be 140 degrees because 4 plus 5, measure of angle 4 plus measure of angle 5 equals 180 because, guys, this is a straight angle right here, right? Straight angle. Measure of angle KLN is 180 degrees. It's a straight angle. So this has got to be 140. Measure of angle 2 plus measure of angle 3 equals measure of angle KON. Okay, also angle addition postulate. Name an adjacent angle to angle 4. Boom. That's adjacent. What does it share a side with? Angle 4. You can highlight it, and that can kind of help you. So it's got to share a side with this one. No angles in diagrams share this side, so we must be talking about something sharing this side, and that's angle 5. Okay, angle 5 is adjacent to angle 4. Last two questions. I'll just quickly bust through them. We got here this question here. State which angles or segments are congruent according to the picture. Again, look at your tick marks, or look at sometimes the way that they'll do it in the book is just number of dashes. So let me show you number of arcs. So let me show you another way that they might do this. If they do this right here, they mean that that angle is congruent to that angle because it has one arc. They also might do this. Just giving you a heads up. Okay, 2 arcs means that these 2 angles are given to us congruent in the textbook. What most people write it out as is this, right, with the tick marks here, okay? So what we can conclude from this is that the angles are congruent. So when we talk about angles, I can say that angle GAM is congruent to angle HAK. Okay, note here, I don't need to put my M in front here because I'm not using equals. I'm using the congruent symbol. So shapes can be congruent to one another, but angle measurements can be equal to one another. I'll think about that for a second. I'll come back to that for sure some other time. Okay, angle MAK congruent to angle GAH is the second one we can conclude. Okay, last one. This is kind of actually comes up on your homework. I'm going to skip this one just for the sake of time. This one here, number 35, comes up in your homework. It's a bit harder, so actually it could be helpful to kind of go through this one with me. When you have something like this, always mark up your diagram. That's my recommendation. Sketch it out. Put it in your notebook, mark it up. You'll figure it out here. Okay, so what we're given to us, we're given that AL bisects angle KAT. So by the definition of angle bisector, what I know here is that if AL bisects angle KAT, I can make the conclusion that angle KAL, okay, because AL is the bisector, so KAL, that's the ray it's bisecting. I can make a conclusion that angle KAL is congruent to angle TAL. Okay, again, TAL. So AT is one of the rays there, yeah, and AL is the other ray. So I know this, by definition of angle bisector, that means that, well, I'd start with this angle KAL. Might just be easier if you draw it in here. Sorry, KAT. It got bisected. What's doing the bisecting? Well, that's AL right here, doing the bisectors. That says that this angle is congruent to this angle right here. So the reason why I marked this up is because this is going to be the same as that. That might be some information that'll come in helpful for us later. Okay, so let's look at the problem here. We're also given that measure of angle 1 equals x. Okay, so this is x degrees right here. And measure of angle 3 is 4x degrees right here. Okay, interesting. So then the question is, on a problem like this, how can I figure out the angle, degree angle of x? Okay, because we're not given any numbers in this problem. Interesting. So I know how to solve for x, right? I've done algebra 1. I'm able to solve for x. How do I get the angle measurement of x here? What can I do? How do I get a number to the problem? Well, this is x degrees. That's 4x degrees. Wait a second. What's this about then? Well, I know that, for instance, this here, SAT, we've dealt with this diagram a lot. This whole thing here is 180 degrees. Okay, whole thing's 180 degrees. So then x here, 4x plus x plus measuring angle KOL would get us to 180 degrees here. But do we know measuring angle KAL? Well, yeah, we do, because it, by definition of congruent angles, right? We already know that these two angles are congruent because the definition of angle bisector told us that that AL creates two congruent angles. So that means this has to be x degrees as well, okay? So what you do in a problem like this, we're gonna take that 180 and that gets a number into the problem, 180 degrees. And it's going to equal, right? It's gonna equal this amount of degrees plus that amount of degrees plus that amount of degrees, right? They gotta add to 180. Because remember, part plus another part, right? This actually has three parts to it, would have to equal the whole. So this isn't exactly the angled addition postulate. It's kind of an extension of that, okay? Now we can solve this. So we take an algebra 1, we should be good to go. We have 1x here. We have another x right here. So 2x plus 4x is 6x. That equals 180. And divide both sides by 6 is how you solve a problem like that. You get x equals 30 degrees. And we're good to go, okay? That's it for me. I sort of announced the homework as well, too. And this is kind of outdated. You're actually not going to do the odds. Check Google Classroom for the homework, because I'm going to post that up pretty soon. I put it in the other video, too, in case you're highly curious. I think you got to do numbers 1 through 21 odds only for the classroom exercises, and also number 32 through 38 all. Okay, this actually isn't homework. This is going to be for Thursday too. I'm going to point that out for Thursday. Okay, and then for your written exercises, you got to do 15 to 20, and then several problems. I think like 22, 24. Anyways, it's on Google Classroom. You can check it out. Anyways, sorry that went so long. And man, this talk wasn't as good as the one that I did last night. I was feeling pretty good about that one, and this was 5 minutes longer. So anyways, hopefully you watched it. Hopefully you got something out of it. We'll figure this out. Take care, guys. Bye.